Hello everyone, my name is Katerina Gonos and I'm Project Engineer at WMG. I've been here for the last 2.5 years working on various aspects of lithium-ion batteries research, and now I'm kind of working on future technologies as well. But before this, I first came to Coventry 6 years ago to study chemistry, a subject that I chose and love because of the way that it explains the physical world and physical processes around us at the atomic level. And we can use this understanding to benefit our lives. So today I have the chance to combine my passion for chemistry and my current work to talk to you a little bit about the elements that could be powering our future. So I'm willing to bet that very close to you right now, you have perhaps a smartphone, a laptop, a watch on your wrist, or perhaps even a set of car keys in your pocket. And if I asked you to consider what all these things have in common, and considering the title of my talk, you probably arrive at the conclusion that they're all in some way battery powered. But just looking at these devices, you can see the batteries come in all sorts of shapes and sizes and different names that denote their different chemistries. For example, lead acid, lithium ion, lithium polymer, alkaline, the list goes on. And these different chemistries suggest that different batteries are not suitable for all applications. One in particular has really been hitting the headlines lately, and that's the lithium-ion battery, even though it's been in a lot of our electronic devices for quite a few years now. So why is it suddenly coming to fame now? Well, many feel that lithium-ion batteries are the key to our greener future. You've most definitely heard of Tesla, but more and more car companies are pledging to go full electric in the next 5 to 15 years. And the lithium-ion battery is the energy storage system of choice for a lot of these car companies. Batteries can also be used in the field of renewable energy to store the energy that these sources can capture, for example, wind turbines or solar panels. And this is critical because it means that we can access this energy during downtime, for example, when the sun isn't shining or the wind isn't blowing. Some people even believe that batteries could keep us in the skies one day, which would be really great because aviation is a major CO2 emitter as well. So that's where they're going, but where did the lithium battery come from? So arguably, it kind of started with Alessandro Volta's zinc and copper battery back in 1800. Since then, the basic battery setup hasn't changed a whole lot. By and large, they're composed of 2 electrodes. In the case of lithium ion, one is graphite and the other is a metal oxide. These are connected by an external circuit that allows electrons to flow and therefore a current to flow when charged particles, such as lithium ions, move between the 2 electrodes. They're able to move between the electrodes because this system is immersed in an organic solvent known as the electrolyte. However, these 2 electrodes don't actually touch, they're separated by a polymer film. So based off this, this general assembly, we've actually achieved around 22 commercial chemistries in the last 200 years, some of which I've listed on the timeline here. I think it's really interesting to note lithium-ion batteries that they weren't really invented in a single eureka moment. It was more a series of small successes and kind of happy accidents, which really is testimony to the very complex interactions that are happening within the battery. So enough history, let's go to the chemistry. And here I have the building blocks of everything I've spoken about so far, all arranged in one convenient periodic table. Out of interest, I've also highlighted some of the elements that have been used in batteries or continue to be used in batteries. So just take a look at them and see if you can identify any patterns in where they are. But obviously the one we're most interested in today is all the way on the left. That is group 1, period 2, lithium. So lithium is the first of the alkali metals, and it's also the smallest and lightest and the least dense. It's also the most electromotive, which means it's very easily oxidized, so it loses its outer electron very easily. So all these factors combined mean that we can create batteries that have very high voltages using lithium and also very high energy densities. And if you've ever seen these videos of batteries catching fire or exploding, it really gives you a crude sense of just how much energy these small devices can contain. Another benefit of lithium is this +1 charge that it has there. Again, as I said, it's caused by losing its 1 outer electron. This means it can move very easily between the 2 electrodes versus other metals which might take on a 2 or 3+ charge. So this is great, but there are some problems. As I said before, lithium has applications with electric vehicles or with stationary storage for renewable energy. But these are two quite different applications and they have different demands. For example, in stationary storage, we don't need as high energy or high power, but we do in general have higher safety requirements. And also we need batteries which have much longer lifetimes than what lithium ion is currently giving us. So it would suggest that lithium ion is in some ways optimized for electric vehicles. But that's not all. This is a periodic table, but not as you know it. It shows the relative abundances of each element on our Earth. And if you look at lithium, you'll see it's in yellow. It's not going to last forever. Although the exact estimates do vary, when we account for the increasing demand from electric vehicles alone, we could easily see ourselves running out of lithium before the end of the century. And what's more than this is that, so it could be easily running out by the end of the century, and we could find ourselves in the same situation that we find ourselves in with fossil fuels today, basically because lithium isn't a renewable resource. So the other issue is that a lot of the lithium reserves are found in poorer or less stable countries, especially in South America. So as demand increases, these countries may try harder to extract and export that lithium, leaving them open to a whole host of political, environmental and ethical issues. For example, in Bolivia, lithium is typically extracted by pouring gallons and gallons of water into salt flats such as these, which brings the lithium to the surface. The problem with this is that it takes water away from local farmers who struggle to provide for their crops or livestock. This water can also contaminate local sources, as has been seen in Tibet several times over the years, and this has killed aquatic life and livestock. So clearly we need to start looking elsewhere, but where to begin? Well, we can start by looking at those two tables again, and if you have a look at them and considering the fact that the element's properties depend on its position in the table, where might we start? If you suggested sodium, then you'd be exactly right. So sodium has a number of benefits over lithium. One of the big ones being that its raw materials are cheaper and cheaper and much more abundant. So sodium is the 6th most abundant element in the world, and a lot of that is found in the oceans. So we can consider this, we can effectively consider this an infinite resource. Sodium-ion batteries are also safer than lithium-ion in many ways, partly because they can be fully discharged, which makes them safer for, to be transported or stored, and this makes them also suitable for, offshore energy storage applications, such as these offshore wind plants that you see here. And another nice thing about the sodium-ion battery is that its basic assembly and operating principle is the same as lithium, which is really good news for industry, as they don't have to spend a lot of money upgrading their machinery or processes to produce this new technology. There are a few downsides to sodium. It doesn't have the same power or energy capabilities as lithium, but you have to realise that it's not, that the focus of research has been on lithium for the last 20 years, not sodium. So it does have some catching up to do, just in terms of years spent on it. And we are already seeing some very rapid advancements. And in addition, if we are looking to use it particularly for the stationary storage applications, we don't need to be reaching the same extreme high power energy that we see with lithium necessarily. So the last 200 years have brought us 22 different chemistries. What will the next 200 bring? Sodium is just one of many possible options being explored, because one thing's for sure, batteries are not going anywhere anytime soon. And because of this, we need to look beyond what's convenient and easy for us if we want to advance our own lives without exploiting others. Because if we are trying to design greener technologies for a cleaner, better world for future generations, then surely that needs to be a better world for everyone, not just the select few.